What I'd like to go over is how do we interact with the pKa of amino acids in order to figure out if they're protonated or deprotonated at a given pH. So during the earlier questions in the problem set, and we went through this in the workshop and in previous videos, we spoke about how when you have some protonated group, so you have some acid HA, and let's give it an arbitrary pKa. Arbitrary pKa is equal to, let's say, 5. What does that mean actually in terms of what does pKa tell us about the acid? What it tells us is how eager the acid is to hold on to hydrogen, how eager the species is, and it could be an R group of amino acid or a nitrogen terminus, a carboxyl terminus, whatever it is that has a pKa of 5, it's saying that that's how much it wants hydrogen. So there's a couple of things that tells us. That means if we have, let's say, again, arbitrary, we have a pH of 7, and we put this HA into the pH of 7. The pH of 7, we can view it as sort of the motivation of the solution to hold on to hydrogen. So again, the pH refers to solution, and pKa refers to an acidic or basic species. pH of 5 versus 7 means that this species with a pKa of 5 is really not that eager to hold on to its hydrogen. It's willing to give up its hydrogen, which means it's relatively acidic, and of course everything is relative, so here we're talking relative to the medium, which has a pH of 7. The pH of 7 tells us that there's relatively low amount of hydrogen in the environment, so this environment is actually quite eager to abscond with a hydrogen when it can. So when the two interact, it means that the environment, so this pH of 7 cup of liquid is going to grab the hydrogen from HA. And so a species with a pKa of 5 in solution of pH 7 is more often than not going to exist in the A- state, and we're going to have free protons, which are basically H3O hydronium ions, or however you want to look at it. So that's one thing that we can do with pKa and pH, is that we can say pH, if pH is greater than the pKa of a species, that species will exist predominantly in the conjugate base deprotonated form. If, conversely, the pH of solution is lower than the pKa, so if the pH was, say, 4 or something, then the acid will exist in predominantly the protonated or conjugate acid HA form. This is important. This is the first application. The second application is, of course, if we have two things. So we have, let's say we have HA and it has a pKa of, I don't know, pK equals 3. And then we have some base. We have some negatively charged species or base or, bicarbonate, whatever. And it has a pKa of 6. What this tells us is, again, it's all, we can view it as strength, okay? So this HA is pretty weak. It's a 3. It's not holding on to that hydrogen with a lot of strength. Now let's make this a B so it makes it so it's a bit clearer. It's not holding on to that hydrogen, so all you need to have is a pKa of 3.2, 3.3, and you'll rip the hydrogen off of HA and it'll become A-. So in this scenario where we have HA and B-, the pKa are 3 and 6 respectively, that B- with a pKa of 6 is going to rip the hydrogen off of HA. HA will exist predominantly in the deprotonated state, and B will become, it'll abscond with this hydrogen, and it will become BH. So that's how I like to think about it, is strength of holding onto the proton, propensity to gain protons, and understand the difference between pH referring to solution and pKa referring to the species. And then again, as a rule, two species interact. If the species with a lower pKa loses hydrogen, the one with a higher pKa gains it. And vice versa. I hope that makes sense. It's fairly simple once you see it a couple of times, but you want to make sure you understand what is a higher pKa relative to a lower pKa. Well, higher is more basic, more likely to grab a hydrogen. Lower is more acidic, more likely to give up a hydrogen. Or lower is holding on to the hydrogen weaker, and higher is holding on to the hydrogen stronger. So in a fight, you know who wins, basically. So let's apply that over to amino acids and how we can tell if they're protonated or deprotonated at a given pH. What I've drawn here is a lysine, and I hope I've drawn it correctly here. But basically, lysine has this NH2 or NH3 on the end of the R group, and the pKa of the R group is 10.5. So what that should tell us is that if the pH of solution is less than 10.5, then, so let's draw this out. If the pH is less than 10.5, implies that lysine has a positive charge. Why? Because there are protons in solution, and the solution has a weaker hold on those protons than lysine does. Lysine holds onto those protons pretty strong, and so it's protonated. And it follows conversely that if the pH is greater than 10.5, then lysine, and here's the important part, not negative, neutral. Why? Well, look at the R group. It goes from NH3 to NH2. It does not go to NH minus. Not easily anyway. So this brings us to how we apply this concept we were speaking about here to amino acids. You have to know what the predominant forms of the R group are. So for example, lysine goes from either positively charged at pH less than 10.5 or neutral at or above 10.5, predominantly. Let's look at over here. I think this is serine, if I'm remembering that correctly. Serine. Yeah, I think this is serine. So it's either serine or threonine. I think it's serine, but at any rate, the pKa here is 13, around 13. So what that means is above 13, the environment is so basic, it deprotonates the hydroxyl group, and you're left with an O- on the end here. So it will have a negative charge at or above pKa 13. But if your pKa, and most of the time it will be, less than 13, you have OH and not O-. So that's important. Students will mess up and they'll say that it's either positive or negative, and you'll completely mess up the charges on your polypeptide. You need to make sure you keep track of what forms does this amino acid actually exist in. Is it neutral and negative? Is it positive and neutral? What's going on? So try to keep track of that. And so I hope that made sense. What you should be able to do after watching this video is relate pKa and pH and apply that to understanding the protonated or deprotonated form of amino acids, and be able to apply that to measuring the overall charge of a polypeptide sequence. If you have any questions, please don't hesitate to let me know.